All right. Which of the following represents the least number of molecules? Well, if I have 20 grams of water, 18 grams of water, that's 1 mole of molecules, right? But I have 20 grams, so that's a little more than a mole. 77 divided by 16, that's going to be even more, right? 77 divided by 16, that is 4.8 moles of that stuff. 68 divided by 42, 100 divided by 44, 84 divided by 20. I guess the first one because the numbers are the closest together, right?
Yeah, that makes sense.
So which of the following represents the least number of molecules? A represents the least number of molecules because it's 20 divided by 18, that many moles, times 6.02 times 10 to the 23rd. So that's 6.6 times 10 to the 23rd molecules. Yeah. Okay. Good stuff. 33. Calculate the following to 4 significant figures. The percent composition of ammonia. So we want to know how much nitrogen and hydrogen, what's the percent composition of nitrogen, and percent hydrogen in ammonia. All right, we want 4 significant figures. So we got our periodic table here. 14.01. That's nitrogen, hydrogen, 1.008. Okay, 3 of those hydrogens, so 1.008 times 3 plus 14.01. All right, so we got 14.01, whoops, plus this number here. All right, 17.034, and we're going to only have 4 significant digits there, 17.03. And now that's our total mass, 17.03. And I'm going to divide my mass of the hydrogen, nitrogen, 4.01, divided by 17.03. And I got 82.23% nitrogen. And the rest, 17.73% hydrogen. Whoops. Okay. And then the next one, the percent composition of sodium thiosulfate or hyposulfate. So let's see, what's the molar mass? We have sodium, 23, 22.99. 2 of those. Sulfur, 32.06. 2 of those. And then 3 16s. Okay. $45.98, 32.06.
That's sulfur.
That's right, times 2. And then 16 times 3,
That's 48.
48. Plus that's the sodium, right?
Yeah.
Plus the sulfur.
Okay. So that's the total, 158.1.
Yeah, we have 158.1, that's our 4 significant digits, grams per mole for the whole compound. And to get the percent sodium, I take my 45.98 divided by that one there. So it's 29.08% sodium. The sulfur, that divided by the total. There we go, 40.56. Okay, and then 48 divided by the total here, 30.36% oxygen. Okay, good. The percent of calcium ion in the calcium phosphate, calcium ion. Let's see, we can probably use Google here to identify the molar mass of calcium phosphate. Molar mass of calcium phosphate.
According to Wikipedia, tricalcium phosphate is a calcium salt of phosphoric acid with the chemical formula Ca.
Okay, 310.18, and then calcium, 3 calciums. Calcium, we have calcium, a molar mass of 40.08. So 3 times 40.08, that over our total mass times 100 will give us our mass percent. So .76% sodium. And that can be sodium ion as well. Mass isn't going to change if it's ion or not.
You lose the electrons, it doesn't change the mass?
Well, it changes the mass, but not enough to make a difference in just with this many significant figures. Remember, an electron is only about almost 2,000th of the mass of a proton or a neutron. Okay. So determine the following to 4 significant figures. The percent composition of hydrogen and nitrogen in hydrozoic acid, HN3. Okay, so here we have 14.01, that's our nitrogen.
Times 3.
Times 3 plus 1.008. All right, so oops. Okay, so the sum of those is 43.038. 43.038 is our mass total, correct?
Yeah.
Now what do we do with that mass total?
Well, we use it to divide the masses of the nitrogen. What was that?
42.03.
42.03.
All right. So 42.03 divided by that times 100. That gives us our mass percent. So it's about 98% nitrogen. Then the hydrogen,
1.008 divided by the 43.00038.
43.038. So it's 2.3% hydrogen. Okay. TNT, nitrotoluene. All right. So C6H2CH3NO23. So looking at that, how many carbons have we got altogether?
7?
I think that's right. So we got 7 carbons. What else do we have?
We got 5 hydrogens.
5, is that it?
I think so.
Yeah, I think you're right. 5 hydrogens. How many nitrogens?
3,
3 nitrogens. How about oxygens?
6.
Is that right? 3 times 2? Yes, 6 oxygen. Okay, so 7 times carbon is 12, right?
Yeah.
7 times 12, what's that, 84?
I don't think so.
7 times 12, 84.
Okay.
Hydrogen 5, nitrogen 3 times 14, 3 times 14, 30, 40, 42.
That's right.
And then 6 times 16. 16, 16, 32. 32 times 3 is 94. Is that right?
16 times 6? 96.
Well, we were close. Okay, so then adding those up, 84 plus 5 plus 42 plus 96, 227. Okay, and so then 84 over the 227, it's about 37% carbon. 5 over the 227, 2.2% hydrogen. And then 42 divided by the 227,
18.5.
18.5% nitrogen. And then 96 divided by the 227.
42.3.
Okay. All right. So we didn't really do 4 significant digits there, but you get the idea. You just put in more values if you want to do 4 significant digits. The percent of the SO42 in Al2SO4 3 minus aluminum sulfate. Okay, so what do we do there?
Just find the mass of the SO42 and put it over the mass of the total?
I think that's what we're trying to do there. Yeah. Let me get Google here. Molar mass of aluminum sulfate. So,
According to Wikipedia, aluminium sulfate is a salt with the formula Al.
okay, I'll double check in here. Got that. Yeah. Okay. So 342.15. Yeah. And then the SO4, the sulfate. Sulfur is, where's the periodic table? Bring it over here. 32.06. So sulfur. That's for sulfur. And for oxygens, 16, 16, 32, 64 for oxygens. So 64 plus the 32.06, 96.06 divided by our total, 342.15.
28%.
Right, 28.1%.
28.1%.
28.1% of that stuff is made of sulfates. Is that right?
Well, there's 3 sulfates.
You're right, there is 3 sulfates. If it was just 1 sulfate, that would be the 28.1%. I think we have to times that by 3, or in other words, we have to take the 96.0 and multiply it by 3. Whoops, 96.06 times 3. And then divide that by the 342.15, which should be the same result as multiplying this 28 by 3, right? So yeah, either 28% is a single sulfate, but 84%, 84.2% of it is 3 sulfates. Okay. All right, determine the percent ammonia in that mixture there.
What is that thing?
Well, it's a cobalt atom and cobalt ion, and that ion is coordinated by 6 ammonia and 3 chlorine. Okay? Well, it's actually probably coordinated by 6 ammonia, and then there's 3 chlorines that are part of that ionic species. So, let's see. We need a cobalt. We need, we want to know the percent ammonia, NH3s. We're going to do that. There's 6 of the NH3. That's 17. So there's 6 17s. So we can keep those together in a group and say 6 of those. And then there's 3 chlorines. The sum of all that will be the total mass, right? Get a little bit better light on the calculator there. All right, so cobalt, 58.93. Ammonia is going to be 1.008 times 3 plus 14.01. So 17.034 times 6, 102.2. And then chlorine is going to be 35.45 times 3 with 106.35. Okay, so our answer is going to be the 102 plus the 106 plus the cobalt.
58.93.
All right, 267.48. Okay, and that's our total mass, and then we just take the 102.2 divided by the 267.5. So about 38.2% of that is our ammonia. Okay. Determine the percent water in the cobalt sulfate pentahydrate to 3 significant figures. Molar mass of cobalt sulfate pentahydrate, not cobalt, copper sulfate. Molar mass of copper sulfate pentahydrate, 249.68. So we got 249.68. That is the total mass. And then we have water is molar mass of water, 18.01.
Water is an inorganic, transparent, tasteless, odorless, and nearly colorless chemical substance, which is the main constituent of Earth's hydrosphere and the fluids of all known living organisms.
That's a good definition. So we got 98, or no, 90, that's a 90.05 divided by our total mass, 249.68. Okay, so we got 36.07% water. Okay, that was easy because copper sulfate was on
Google?
Yeah. All right, 37. Determine the empirical formula for compounds with the following percent compositions. All right. So do you remember how to do these empirical formula ones?
Well, what's the empirical formula again?
The empirical formula is the simplest chemical formula for a compound. So if the chemical formula, for example, is C6H12, the empirical formula would be CH2, right? So what we call this is the molecular formula, and this is the empirical formula. Okay, so it's the simplified, simplest whole number ratio. All right, ionic compounds should always be in the simplest whole number ratio, but molecular compounds can exist in different ratios. So sometimes it's possible to have compounds that have chemical formulas like this, and it's also possible. Well, a better example is CH4, no, that won't work. CH4, C2H6, CH3. Let's see. I'm trying to think of substituents that would, I mean, it's possible, but let's see. So C4H, um, 10, C2H5. No, that doesn't happen. But if our empirical formula is this, the molecular formula could be C4H10, but it could also be C8H20, for example. Okay? All right, so empirical formulas are molar ratios of the elements, right? Just like molecular formulas or chemical formulas are molar ratios. This means there's 6 moles of carbon, 12 moles of hydrogen. You could also think of it as the number of atoms of the material, substance. Okay?
And the percentages correspond to those molar ratios?
Well, no, not exactly. The percentages don't correspond to those molar ratios, and that's just a little wrinkle that we have to remember. When we say 15.8% carbon, 84.2% sulfur, what we're saying is that by mass, if I had a 100-gram sample, okay, so I like to draw a little picture of a sample of our compound that we're interested in. This is some sort of a CXSY, right? I don't know the chemical formula exactly, right? But I know it contains carbon and sulfur. I don't know its molar ratios, and so X and Y are those values for now. But if I had 100 grams of it, 100 grams of this, then I would know that 15.8 of those grams would be carbon, and 84.2 of those grams would be sulfur. Okay, that's what that percentage means. And I can go from grams of carbon to moles of carbon, and from grams of sulfur to moles of sulfur, right? Because there's 12 grams of carbon for every 1 mole of carbon, all right? So 15.8 divided by 12 tells me that I have 1.32 moles of carbon there. 84.2 grams of sulfur to moles of sulfur, that's 32.06 for every mole. So 84.2 divided by 32.06, and
2.63?
Okay, 2.63 moles of sulfur.
Can you use those numbers now?
Yeah, I can. I can say C 1.32, S 2.63.
But that's not the end, right?
No, that's not it. We're not done yet. We need to now find the simplest whole number ratio.
Oh, I remember this part. Divided by the smallest number.
That's right. If we divide by the smallest number, it makes one of them go right to, this is 1.32, sorry, go right to 1. So if we did that, then I would have C1 2.63 divided by 1.32. That's 2. So I have C1 S2, or CS2 as our empirical formula. So from the mass percent, I convert those masses, use those as if I had a 100-gram sample, convert those masses to moles, and then I get the molar ratio and simplify it to a whole number ratio, and that will be my empirical formula. Let's try that again on this next one here.
So 40 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen?
That's right. 40 grams of carbon. How much did you say?
6.7.
6.7 grams of hydrogen. 53.3
0.3.
grams of oxygen. All right, now what do I want to do with those?
Convert them to moles.
That's right. I want to go moles of those. Why do I want to go moles?
Because that's what the empirical formula is. It's the molar ratio of those different elements.
That's right. Good. This one's always easy, right? 6.7 moles of hydrogen is 1.008 grams for every 1 mole, so it's essentially that for 2 significant figures for sure. 12 grams for every 1 mole, 16 grams of oxygen for every 1 mole of oxygen. Okay? So 16, turn that into a 6 a little better, there we go. So 53.3 divided by 16, and we get 3.33, and then 40 divided by 12, 3.33 as well. Okay, so C 3.33, H 6.7, O 3.33.
It's CH2H2O.
What?
CH2O.
Okay, so you saw that if I divide these by the smallest,
Yeah, it's going to be CH2O.
C, H is 2, and then oxygen is O. Good job. So that's our empirical formula. Okay, good. Now we're doing determine the empirical formula for some more compounds here, given the percent composition. All right. 43.6% phosphorus, 56.4% oxygen. How are we going to approach this one?
Just pretend like you have a 100-gram sample.
So if I had a 100-gram sample, so here's some of that material, that phosphorus and oxygen, 100 grams of it, how much of this would be phosphorus?
43.6 grams.
All right, so 43.6 grams would be phosphorus. And the rest of it
Yeah, 56.4 grams.
would be what?
Oxygen.
Okay, and I want to identify how many moles of those I have, right? Why do I want to go to moles?
Because you want the molar ratio to get the empirical formula.
Yes, that's right. 16 grams of oxygen for every mole. Oh, this is phosphorus. Mole of phosphorus. It's not 16. This is 16 grams of oxygen for every 1 mole of oxygen. What's phosphorus?
Phosphorus, can you see the periodic table?
You have yours?
It's 30.97.
Okay, so we'll put that in here real quick. What'd you say?
30.97.
30.97. So I'll do 43.6 divided by 30.97. And we got 1.41 moles of phosphorus. 56.4 divided by 16. 3.53 moles of oxygen. Sorry, did I say phosphorus? Yeah, 3.53 moles of oxygen. So P 1.41, O 3.53.
Divide by 1.41.
So dividing by the one that's the smallest forces one of them to 1, right? And so we can helps us simplify. 3.53 divided by 1.41.
2.50. Oh, that's not a, does that round up to 3?
No, it's pretty close to right at, I mean, it's half of 5, right?
Oh, so you multiply both by 2.
That's right, and multiply both by 2 to get this to a whole number as well. So P2O5 then ends up being our empirical formula. Okay, good. Let's do the second one there. 28.7% potassium, 1.5% hydrogen, 22.8% phosphorus, and 47% oxygen.
Just pretend like you have a 100-gram sample.
Same thing, 100-gram sample. So I start off with 28.7 grams of potassium, 1.5 grams of hydrogen, 22.8 grams of phosphorus, 47.0 grams of oxygen. This 16 grams for every 1 mole of oxygen. This one here, phosphorus. What did we say phosphorus was?
30.97.
So 30.97 grams of phosphorus for every 1 mole of phosphorus. This one's just 1, right?
Yeah.
And this is what? Potassium?
Potassium. Let's see. 39.10.
39.10 grams of potassium for every 1 mole of potassium. Where'd you get that?
The periodic table.
Okay. So we got moles of potassium. Okay, sorry. Moles of hydrogen, moles of phosphorus, and moles of oxygen. Okay. So 28.7 divided by 39.1. 0.734, 1.5 there, 22.8 divided by
30.97.
0.736, and then 47 divided by
16.
2.9375. All right, so we got K, H, P, O. Whoops, let's get a little bit lower here. K, H, P, O. 0.734, 1.5, 0.736, 2.975. It looks like if we divide all of them by 0.734,
Because that's the lowest number?
right, phosphorus will be 1. 1.5 divided by 0.734. That's 2. H2, P, and oxygen, 2.97 divided by 0.734. That's 4. There it is. KH2PO4. That is potassium dihydrogen phosphate. Okay, good.
All right. 39, right?
Okay, yeah, 39. The compound of carbon and hydrogen contains 92.3% carbon and has a molar mass of 78.1. What is the molecular formula?
Molecular formula. How do you do that one?
Well, let's talk about that. So if I have a information, a mass percent composition of my compound, 92.3% carbon. So again, I'm going to assume 100 gram sample to simplify things for us. 92.3 grams of carbon. I'm after the molecular formula. Molecular formula is also the whole number ratio, but it's just not the simplest whole number ratio, right?
Yeah.
Okay, so I need to know the mass of the different elements in my compound. Oops. It said it had hydrogen in it, right?
Yeah.
So a compound of carbon and hydrogen, only carbon and hydrogen. So 100 minus the 92.3 will be our 7.7% will be our grams of hydrogen. So that's 7.7 moles of hydrogen.
How'd you do that?
Remember, grams of hydrogen, moles.
Oh, yeah.
So it's just 1.008 grams for every 1 mole. And then carbon, 12 grams of carbon for every 1 mole of carbon. So 92.3 divided by 12, 7.7 moles of hydrogen. Looky there.
Oh, they're the same, huh?
That's right. So the empirical formula is C 7.7, H 7.7.
Well, then you divide it by 7.7.
That's right. Divided by the smallest, right? So it's CH. That's our empirical formula. But that's not the answer, is it?
No, they want the molecular formula.
Okay, so I get the molecular formula now by knowing the relationship between, whoops, where were we at? Oh no, I did it again. There we go. We get our molecular formula by knowing the relationship between the empirical formula and the molecular formula. Okay, so we have our empirical formula, CH. Now we're going to give ourselves a fresh paper to remind ourselves of the relationship between the empirical formula, CH, and the molecular formula. Okay, we don't know the molecular formula. What else? What information do they give us?
They give us the molar mass.
All right, or the molecular mass, we can call it, because we know this is a molecule. And that same relationship between the empirical formula and the molecular formula, it exists between the empirical mass and the molecular mass, or the molar mass. And they gave us the molar mass of 78.1, right?
Yeah. What about the empirical mass? Where do you get that?
Well, the empirical mass, you can hear that name, the empirical mass. It's just the mass of the empirical formula.
Oh, okay, so that's 12 and what, 13?
That's right, 13. Very good. So the empirical mass is 13. The empirical formula and the molecular formula, they relate to each other by a multiplier. We usually call that multiplier n. And we don't know what n is. Whatever n is, you'd multiply it by the ones down here to get the molecular formula. But we can solve for n, the multiplier, by taking 78.1 and dividing it by 13. So that'll be 6 here. Tells us that this is 6, so the molecular formula has got to be what?
C6H6?
That's right, C6H6. So they gave us the molecular mass, and we could solve for the empirical formula.
How did we get the empirical formula?
Remember, by taking the masses.
Oh, yeah.
Okay, did all this. So once we have the empirical formula, we also can get the empirical mass and find the multiplier if they give us the molecular mass.
Okay, I got it.
All right, I think we're going to have another opportunity to practice that. Number 40 here, dichloroethane, a compound that is often used in dry cleaning. Contains carbon, hydrogen, and chlorine. It has a molar mass of 99, and an analysis of the sample showed it was 24.3% carbon, 4.1% hydrogen. What's the molecular formula?
What percent chlorine?
Well, if chlorine's what's left, it's got to be 100 minus the 24.3 and minus the 4.1, right?
Oh, yeah, okay.
So we can assume a 100-gram sample, 24.3 grams of carbon. In a 100-gram sample, that's how much carbon there would be, right? 4.1 grams of hydrogen. That's moles of hydrogen right there, right? And then 12 grams of carbon for every mole of carbon. 1 gram of hydrogen for every 1 mole of hydrogen. Okay? So 24.3 divided by 12, that's going to be 2, right?
Pretty close.
2 moles of carbon, 1 mole of hydrogen. So CH2 so far, right?
Now we got to do chlorine?
Yeah, we got to do chlorine. So if we take 100% and we subtract the, 24.3%?
Yeah. And then the 4.1.
Minus the 4.1, and we get 71.6. 71.6%, which would be, that's how many grams of chlorine there would be if I had a 100-gram sample. 35.45 grams of chlorine for every mole of chlorine. So 71.6 divided by 35.45, just double checking on the periodic table there. So that's also 2. So, it was 2 moles of chlorine and 1 mole of hydrogen. So C2H, no, it's 4. What am I saying? 4. C2H4O, or Cl2. All right, so let's try that again. CHCl, 2, 4, 2. Okay, there we go. What's the name of the compound? Dichloroethane. Dichloro sounds like 2 chlorines, huh? Let's see, what is the molecular formula? Now that is the empirical formula for sure. And now we want to see if it's also what the molecular formula for the compound might be. C2H4Cl2. All right, there's our empirical formula. And the empirical formula relates to the molecular formula through a multiplier. I don't know what the molecular formula is, and we don't know what the multiplier is.
The molar mass, what is that?
Let's see, what is the molar mass for the compound?
It says it's 99.
Oh, 99. So the molar mass is 99 grams per mole. And the empirical mass, we can figure that out by adding these together. So if I add together 2 12s, 4 1s, and then 35 times 2 is 70, so about 71 for 2 chlorines, I get 99. All right. So what does that tell us?
The empirical mass is the same as the molar mass? How can that be?
Well, it just means that the multiplier here is what?
Oh, 1?
That's right. And if n equals 1, then the molecular formula is C2H4Cl2, right? So the empirical formula and the molecular formula are the same in this case. Okay, good stuff. Determine the empirical and molecular formula for chrysotile asbestos. It has the following percent composition. Want to read them off to me?
28.03.
And I'm just going to say grams because I'm going to pretend like we have a 100-gram sample, okay? What is that stuff?
Magnesium.
Okay. And then what's the next one?
21.6
What?
grams of silicon.
Grams of silicon. And then next?
1.16 grams of hydrogen. And then 49.12. 21 grams of oxygen.
Okay, there you go. Good job. All right, so then we go grams of oxygen to moles of oxygen, grams of hydrogen to moles of hydrogen.
That's just 1.16.
Okay, 1 to 1. So 1.16 moles of hydrogen. All right, magnesium.
24.31.
All right, 24.31 grams of magnesium for every 1 mole of magnesium. Silicon is 28.09.
28.09 grams for every mole.
That's right. Okay, so what do we got here? We got 16 grams of magnesium for every mole. So 28.03 divided by 24.31, and that is 1.15 moles of magnesium. Okay. And then we got silicon, 21.6 divided by 28.09. So we got 0.769 moles of silicon. We did hydrogen already. It was just 1, right? So 1.16.
49.21 divided by 16.
Okay. That's 3.1 moles of, what was this last one?
Oxygen.
Oxygen, okay. Okay, so with those values, we can find an empirical formula. All right, so we know that we have Mg 1.15, Si 0.769, hydrogen,
1.16. Just like the magnesium.
oh yeah, oxygen,
3.1.
okay. Now I divide them all by what?
0.769.
Oh, because that's the lowest. So 1.15 divided by 0.769, that is 1.5. So Mg 1.5, Si 1, H 1.5, oxygen 3.1 divided by,
0.769.
that's 4.
Now you got to multiply everything by 2.
What do you mean?
Well, because it's 1.5, you need a whole number.
Okay, so we're not quite there yet. 1.5 can be multiplied by 2, so we got Mg3, Si2, H3O8.
Yeah.
Okay, there we go. There is our empirical formula for, oh, look, they gave us, they don't want the empirical formula, or they don't want just the empirical formula. They want the molecular formula, too. I didn't know this compound was a molecule, but they say that its, its molar mass is 520.8 grams per mole. 520.8 grams per mole. So the molar mass is given to us at 528 or 520.8 grams per mole. The empirical mass, we'll find that out by adding this stuff together. The empirical formula, Mg3Si2H3O8, and the molecular formula we're going to find that out by finding out what our multiplier is here. Okay, so 3 magnesiums, that's 24 times 3, 24.31 times 3. 2 silicons, that's what?
28.09 times 3
Times 2?
times 2.
Okay, so there's the mass from the magnesium, there's the mass from the silicon. 1.5 is the mass from the hydrogen. And then 4, 16, 16,
64.
64 grams for the oxygen.
Yeah.
So this is the mass for the magnesium. This is the mass for the silicon. 1.5 is the mass for the hydrogen. 64 is the mass for the oxygen. Did I do that right?
Think so.
So 194.61 and 520.8 is the molar mass. So 2.67. 2.67. 24.31. 2.67. That's an odd number. A weird number. 2.67. What did we do wrong? Oh, 520.08. Let's add this up again. A magnesium, 24.31 times 3. Oh, there's just one silicon. There's just one silica here. There's not two. So add one silica to that, 28.09. There's 3 hydrogens. Did I do that last time? I don't think I added 3 hydrogens last time. I just added 1. And then plus the 16, 16 is 32. 32. Oh, I was looking at this one here. I don't know what I was doing. So we need 16 times 8. So 120. So 120 plus this one here, which is the sum of the magnesium, the silicon, and the hydrogen. So 232.02. Let's try that. 232.02, so 520.8 divided by that, 2.24. Let's see if we did that right. 24.3 magnesium. I had to multiply that by 2. Oh, no, there is 2 silicons. There is 2 silicons. Did I do 2 silicons? Multiply that by 2, multiply that by 2, multiply that by 2, multiply that by 2. So there's 3 magnesiums, 24.3 times 3. So the magnesiums is 72.9. 2 silicons, 28.09. So that's 56.18. 3 hydrogens, 3.00. 8 oxygens. 8 times 16 is 120. 8. So 128 plus 3 plus 56.18 plus, oh no, what does that say? 72.9? Yeah, plus 72.9. 260.08. That looks good, right? 520.8 divided by 260.08. There we go.
You kept making mistakes.
Yes, I did. It all comes from not writing down clearly and being confused by leaving this up there, right? So we found that N is 2 here. Our multiplier is 2. So our molecular formula is what?
Mg6Si4H2O. How many hydrogens?
H3.
H6. O16.
Okay. Crazy species there. Chrysotile asbestos. I'm not sure if I would call that molecular. Yeah, I don't think I would call it's not its molecular formula. So I don't think that's a molecule. I mean, it has a metal in it there. Doesn't make sense as a molecule. I think that is probably a kind of a hybrid compound, but its chemical formula would be better than calling it its molecular formula. Okay, next. Determine the molarity for each of the following solutions.
Molarity? What's that?
You don't remember molarity?
Well, I think I remember it from class a little bit.
So molarity is abbreviated big M.
Oh, it means moles?
Not moles. Moles per liter.
Oh, moles per liter.
All right. So we want to know how many moles of our solute, the thing being dissolved in our solution, there are, right? So moles of solute, liter of solution. Okay. Almost always in chemistry, the solution is going to be water in general chemistry, right? So the solvent, sorry, is going to be water, and the resulting solution is aqueous, right, made in water. So let's see here. If we have 0.444 moles of cobalt-2 chloride in 0.654 liters of solution. So I want my units to be in molarity, and I start with 0.444 moles of cobalt-2 chloride, and I want liters down here, liters of solution, that's 0.654.
Do you need anything above that?
I don't. I just need to make sure my units line up to get the moles per liter. So 0.444 divided by 0.654. All right, so 0.679 molar, that's our solution's concentration. Okay. Next one, 98 grams of phosphoric acid in 1 liter of solution.
What do you do if you start with grams?
Well, I remember that I want molar again, which is moles of solute per liter of solution. Okay. And then I start with my 98.0 grams of H3PO4. And I can convert that to moles by going from grams of H3PO4 to moles of H3PO4. All right, I'll use Google here. Molar mass of phosphoric acid?
97.99 grams. According to FHSDFHHS.sharpschool.net, the molar mass is obtained by adding up the average atomic masses of these atoms.
Okay,
Molar mass
so
H3PO4
we start with that many grams, and now I've converted it to moles, and that's what I want. Moles of my solute, right, which is the phosphoric acid. The resulting liters of solution is in 1 liter. Liter of solution. So 98.0 divided by, oh look, it's the same. So it's going to be 1 mole. That divided by 1 is going to be just 1 mole per liter, or 1 molar. Right, 1 molar solution. Okay, next.
0.2074 grams of calcium hydroxide in 40 mils of solution.
All right. So I want my units on the right to be what?
Moles per liter.
That's right, moles per liter, because that's what molarity is, right? And we want to find the molar concentration of the calcium hydroxide in solution. What's on the top left here?
Your grams of calcium hydroxide?
Very good. Grams of calcium hydroxide. How much is it?
0.2074.
All right. And then I can go from grams of calcium hydroxide to moles of calcium hydroxide. Okay. Molar mass of calcium hydroxide.
inorganic compound with the chemical formula Ca.
All right, so it's 74.1 grams for every mole. So if I go 0.2074 times oh, there we go. Times divided by 74.1. 0.0027, 0.00279. That's moles, but we're not done yet. I shouldn't have stopped there. That's for every 40 milliliters of solution. Now, milliliters needs to be in liters, so I'm going to convert milliliters to liters here. There's 1,000 milliliters for every liter. Okay? I don't need anything up here, so don't let that bother you, because I'm just trying to get these units to come out this way, moles per liter. Started with grams, converted it to moles, so I got moles on top. Started with milliliters on the bottom, converted it to liters, so now I got liters on the bottom. The milliliters cancel out. All right, so I divide by, I took the 0.2074, divided by 74.1, divide by 40, and times 1,000. So 0.070. How many significant figures? 3 significant figures. So 700 molar calcium hydroxide. That's the concentration. Okay. D. 10.5 kilograms of sodium sulfate decahydrate in 18.6 liters of solution, right? So what goes to the right of my equal sign?
We want to determine the molarity.
All right, so we want molarity, which means what?
The moles of solute, sodium sulfate decahydrate.
Very good. We want moles of sodium sulfate decahydrate for every liter of the solution. Okay? So, I start with what?
10.5 kilograms.
10.5 kilograms of my, this is a long one. I'm just going to say sodium sulfate. Is that okay?
Okay.
N for Na. I'll say NaS, sodium sulfate. But it's a decahydrate, so let's see if we can find the molar mass of sodium sulfate decahydrate molar mass.
322.19 grams per mole, according to some information I found on EMD millipore.
Double checking the chemical formula there. Looks good. 322.2 grams per mole. Yeah. So, let me write that down. 322.2 grams per mole. That's our molar mass of our sodium sulfate decahydrate. Important to remember. But this is in kilograms, so I need to get it into grams because I can convert grams to moles. So I go from kilograms to grams, 1,000 grams for every kilogram. And then I go from grams to mole.
327.2?
327.2. No, 322.2. 322.2. 322.2 grams for every mole. And there we go. Now I got moles on top. Now I just need liters on the bottom. How many liters did it say?
18.6.
18.6 liters of solution. Okay, so 10.5 times 1,000 divided by 322.2 divided by 18.6, so 1.75 moles of solute per liter of solution. Okay, good stuff. Just double checking in the book. That one's kind of tricky. Lots of terms there. Okay, the next one, that many moles of I2 in 100 milliliters of solution. Well, that's not too hard if we just want iodine or molarity, right? To the right of our equal sign, what do we write?
Moles of the, is the iodine the solute?
Yeah, moles of I2 for every liter of solution, right? So starting off with 7 times 10 to the minus 3 moles of I2. So we already got moles of I2, that's good. And then we just have 100 milliliters. Is it okay if I put 0.1 liters just like that, if I see 100 milliliters?
It's not the right significant figures, but okay.
Yeah, so I need 1, 2, 3, 4 significant figures. Okay. This only has 1 or 2, I guess, so it's not going to, we're only going to get 2 significant figures. But yeah, what I did is I did the milliliters to liters in my head, right? 100 milliliters is 0.1 liters. So 7 times 10 to the minus 3 divided by 0.1. So it's 0.07 molar solution. 0.07 molar solution. Okay. And then we have one more down here. We do. F. 1.8 times 10 to the 4th milligrams of HCl, 0.075 liters of solution. Okay. So, molarity. We want moles of HCl for every liter of solution. And start off with how much?
1.8 times 10 to the 4th. Is that 18,000?
I think so. 1.8 times 10 to the 1, 2, 3, 4
Milligrams.
milligrams of what?
HCl.
Okay. And only 2 significant digits there on both of those questions, so we're going to have 2 in our answer there. So 18,000 milligrams. I can go to grams though, right?
Yeah, that's 18 grams.
Okay, so for those folks at home who still struggle with that, I go from milligrams to grams, 1,000 milligrams for every gram. That'll get me in grams. Now, why did I go to grams?
Because the molar mass is in grams per mole, not milligrams per mole.
Yeah. So HCl is, chlorine is 35.45 plus 1, 36.45. So 36.45 grams for every 1 mole. All right. So 18,000 divided by 1,000, which is just 18, divided by 36.45, 0.4938. But that, I'm not done yet, am I?
No, you're just in moles of HCl. You need to get liters down there. It's 0.075.
So 0.075 liters of solution. So I divide that by 0.075, and that gives me my molarity of 6.6 molar. Double check in here. Yeah, 6.6 molar. Okay, good stuff. 48. Determine the molarity of each of the following solutions. So we have lots more of these to do, which is a great exercise. So a molarity of 1.457 moles of KCl and 1.5 liters of solution.
That's easy.
Well, it's easy because we've been doing it, but somebody might just come to this one and not know it, so we got to give them the whole show.
Well, you just take mole. You want moles per liter.
Moles of what?
KCl in this case, solute per liter of solution.
All right, and then what?
Well, just start with how many moles they gave you. 1.457
Of what?
KCl.
Divided by
1.5 liters.
1.5 liters of solution. So that's that 1.457 divided by 1.5. So my molarity is going to be 0.971. All right.
Okay, the next one is grams, so you just got to convert that to moles, and then divide that by 1.
All right. So molar mass of sulfuric acid is what we're going to look for, right? Molar mass of sulfuric acid, 98.079.
Sulfuric acid or sulfuric acid, known in antiquity as oil of vitriol, is a mineral acid composed of the elements sulfur, oxygen, and hydrogen, with the molecular formula hydrogen sulfate.
So I go 98.08 grams of H2SO4 for every 1 mole of H2SO4. And then I need the liters down here, 1 liter. So it's 0.515 divided by 98.08 divided by 1, so it's 0.005. 3 significant digits? Yeah, 0.00525, or 5.25 times 10 to the minus 3 molar H2SO4. All right, what's next?
Aluminum nitrate.
We have a solution of aluminum nitrate. Molar mass of aluminum nitrate.
According to Wikipedia, aluminium nitrate is a white, water-soluble salt of aluminium and nitric acid, most commonly existing as the crystalline hydrate, aluminium nitrate monohydrate, Al9 hydrogen oxide.
So aluminum nitrate for every liter of solution. Right, that's what molarity is. Big M is moles of solute per liter of solution. Okay, and I start with 20.54 grams of aluminum nitrate. And I'm going to go from grams of aluminum nitrate to moles of aluminum nitrate. All right, 212.996 for every mole. And then I have moles of aluminum nitrate on top. I just need liters of solution down below.
1,575 milliliters.
All right, that's 1.575 liters, right? But for those of you who are still struggling with that, we'll start with 1575 milliliters. And I can get rid of milliliters into liters. I want liters on the bottom. So I have 1,000 milliliters for every liter, like that. So 20.54 divided by 212.996 divided by 1575 times 1,000, and that's 0.0612 moles of aluminum nitrate. Okay, so on to letter D, right?
Yes, 2.76 kilograms of copper sulfate pentahydrate. Is that what that is?
Yeah, copper sulfate pentahydrate in 1.45 liters of solution, right? So I will molar mass of copper sulfate pentahydrate. So it's 249.68 grams per mole. And we're starting off with 2.76 kilograms, and it's going in 1.45 liters. So what do I want to write in my equal sign?
Molarity, moles of copper sulfate pentahydrate per liter of solution.
Okay, moles per liter. Moles of my solute per liter of solution. And I start off with 2.76 in kilograms, and I can go from kilograms to grams, and then I can go from grams to moles, right? So 1,000 grams for every kilogram, 249.68 grams for every mole. Now I'm in moles with my copper sulfate, right? Kilograms are gone, grams are gone. And then I need my liters of solution down below.
1.45.
1.45 liters of solution. Not much easier than that. So 2.76 times 1,000 divided by 249.68 divided by 1.45. So 7.6 molar, 7.62 molar copper sulfate pentahydrate. Now, that would be a pretty difficult solution to make because that's a lot of copper sulfate pentahydrate dissolved in that water. It'd be doable though. You have to probably heat it up and maybe stir it for a long time, but heat it up also to help the solubility. But it'd probably work. Okay. B there. Look at that. They told us how many moles and they told us how many milliliters, but we can convert that to liters in our head almost, right? So we'll go from moles, 0.005653 per liter divided by 0.01. That's 10 mils. So 0.5653 is the molarity for E.
How did you do that?
I just put the moles over the liters, and that's 10 milliliters. Okay, so F. Grams of glycine, 1.5 milliliters of solution. Molar mass of glycine,
According to Wikipedia, glycine is an amino acid that has a single hydrogen atom as its side chain.
0. Let's do 8.89 times 10 to the minus 4 grams of glycine. I just need to get moles of glycine for every liter of solution. It's 1.05 milliliters. Okay, so I could do that in my head, but that might not be comfortable for some. So we'll go from grams of glycine to moles of glycine. Well, I want moles of glycine on top, right? Molar mass, it says, is 75.07 for every 1 mole. So 8.89 times 10 minus 4 divided by 75.07. That'll give us moles of glycine divided by liters of solution, 1.05 milliliters. And there's 1,000 milliliters for every 1 liter. Okay, so 8.89 times 10 to the minus 4 divided by 75.07 divided by 1.05 times 1,000. So 0.0113 molar glycine in solution. Okay. 49. What is the mass of solute in a half a liter of 0.3 molar glucose? Okay, so what is the mass of solute? What goes to the right of the equal sign?
Oh, we want mass of solute. What's the solute?
Let's see.
Oh, it's the glucose.
That's right. So I want mass of solute, grams of glucose. Is that okay?
Okay, grams of glucose.
And what am I provided?
You have the volume of solution and the molarity.
And I want grams. Okay? So this isn't necessarily clear in any of your guys' minds at this point. But if we recognize that we're given molarity, which is moles of glucose, it's 0.3 moles of glucose for every liter of solution, right? And the molar mass of glucose I see is 180 grams per mole, right? So I have moles of glucose. I can use this to go to grams of glucose. So if I had moles of glucose, I could go to grams of glucose with this. I have liters of solution. That's how many moles there are per every liter of solution. And I'm told that I have 0.500 liters of solution. So liters can cancel out. I'll have moles, and then I can convert moles to grams. Okay? So after you practice sometimes, it's easy to kind of see what needs to happen. But if you are starting off, it's not easy. That's all right. You just start with something. You can make mistakes and then you gradually understand. Another thing you could do is work from this side over here. If I know I want grams of glucose at the end, and there's 880 grams of glucose for every mole of glucose, I can put that up here. Say, 180 grams of glucose are in every 1 mole of glucose. Now I need to get rid of the moles, and I see I have this, so I can put 0.3 moles of glucose for every 1 liter of solution. And then I see I need to get rid of liters of solution because I want just glucose by itself, grams of glucose, and I have that 0.5 liters of solution. So you can work backwards to help yourself out. And that's absolutely fine. Let me show you another thing that you might do. You might think I need grams of glucose. And you might say I have 0.3 moles of glucose given to me for every liter of solution. And then you can sit and look at that and say, okay, I can go from moles to grams. Moles of glucose for every gram of glucose. 180 grams for every mole, right? So moles are gone and you're left with grams. But now I need to get rid of liters, and so you can put 0.5 liters of solution up there like that. They'll both give you the same answer. All right. If you thought I want grams of glucose and I need to, I don't know where to start. I know I have a half a liter of the glucose solution with the solution there. Then that might prompt you to think, I know that there's 0.3 moles for every liter. So I can put the 1 liter contains 0.3 moles of glucose. All right, so this is every liter of solution has 0.3 moles of glucose. And then I might see that, oh yeah, and then I can go from moles of glucose to grams of glucose, because there's 180 for every gram. All of these would give you the same answer, right? So your thought process, there's a lot of flexibility, but the key is looking at the units and remembering your goal. So if you don't start off by writing what your units are after and giving yourself some platform to experiment with, to work on, you'll be in trouble. All right, so let's do this one. What do we do?
0.5 times 0.3 times 180.
Okay, so it's 27 grams of glucose for every half a liter of the 0.3 molar solution. Okay, good. 51. Calculate the number of moles and the mass of solute in each of the following solutions. Moles and mass. Moles and mass. Okay, so if I have 2 liters of 18.5 molar sulfuric acid, H2SO4, yeah, 2 liters of 18.5 molar concentrated sulfuric acid, I can start with I want to know how many moles of H2SO4, let's say. I'm also interested in knowing grams of H2SO4, right? So for moles, start off with 2 liters, 18.5 molar. Which one should I write down first?
Does it matter?
Actually, I don't think it does matter. I don't think it matters. I think we'll be okay either way. Because if I write down the liters first, liters here, 2 liters, I go 18.5 moles per liter. Liters cancel out like that. If I started off with 18.5 moles for every liter, and then I multiplied it by my 2 liters, I'd end up with the same units, right? Okay. So 2 times 18.5 is how many moles of H2SO4 I'm going to have. And now if I want to take that to 37 moles of H2SO4, so now if I want to take that to grams, I mean, if I had wanted to start from the beginning again, I would just go 2 liters, 18.5 moles for every 1 liter. And then I would say, let's find the molar mass of sulfuric acid real quick. Molar mass of sulfuric acid, 98.
According to Wikipedia, sulfuric acid or sulfuric acid, known in antiquity as oil of vitriol, is a mineral acid composed of the elements sulfur, oxygen, and hydrogen, with the
98.08
molecular formula hydrogen sulfate.
grams of H2SO4. So just 37 times the 98.08, or we can do it again. Yeah, there it is, right? 2 times 18 times 98.08. Okay, so 3,628 grams of sulfuric acid and 37 moles of sulfuric acid. So let's do this one a little bit differently. The next one, where we're looking at sodium cyanide, 100 milliliters, 3.8 times 10 to the negative 5 molar, which is the minimum lethal concentration of sodium cyanide in blood serum. So how many grams and moles of the sodium cyanide are in that 100 mils of solution, right? What goes to the right of our equal sign?
Moles?
Yeah, let's start with moles of the sodium cyanide, right? Then what?
We could start with 3.8 times 10 to the minus 5, or the 100 milliliters.
I'll go with 3.8 times 10 to the minus 5. That's moles for every 1 liter, right?
Is that moles or moles per liter?
Big M, right? Big M, so it's moles per liter. Okay. All right. 3.8 times 10 to the minus 5 moles for every liter. And then I go from moles to, because this is moles, this shouldn't be big M, it's moles per liter. Big M is moles per liter, so you shouldn't go big M per liter. Moles per liter. And then I go moles to grams. Oh, no. I want to keep moles on top. I just multiply by liters, right? Because I just want moles. So I just need to multiply by the liters, which is how much? 100 milliliters. And I'll convert milliliters to liters by going 1,000 like that. So 3.8 times 10 to the minus 5 times 100 divided by 1,000. So that's 3.8 times 10 to the minus 6 moles of sodium cyanide. And then we'll go from moles of sodium cyanide to grams of sodium cyanide. Molar mass of sodium cyanide.
According to Wikipedia, sodium cyanide is a poisonous compound with the formula sodium cyanide. It is a white,
49.01.
water-soluble solid.
All right, so that's how many moles there are, and 1.86 times 10 to the minus 4 grams of sodium cyanide. Okay? Minus 4. Okay, good. All right, 13.3 molar formaldehyde. What's the molar mass of formaldehyde?
According to Wikipedia, formaldehyde is a naturally occurring organic compound with the formula carbon dihydride O. The pure compound is a pungent-smelling colorless gas that polymerizes spontaneously into paraformaldehyde. Hence, it is stored as an aqueous solution, which is also used to store animal specimens.
So I would want to know what? What do I want to write in my equal sign?
It says calculate the number of moles in grams.
All right, so I'll start with moles of formaldehyde. Here I have 5.5 liters. We'll start with the liters first this time. It's okay to start with the molarity as well. And there's 13.3 moles for every 1 liter. That's what Big M says of the formaldehyde. Okay, and that'll give me moles of formaldehyde, which is all I want to do. So 5.5 times the 13.3. True?
Yes.
Okay. 73.15 moles of formaldehyde, and now I got to go to grams of formaldehyde. So I go from moles to grams, 30.03 for every gram. So times 30.03. So 2,197. Three significant figures, 2020, 2.20 times 10 to the third grams of formaldehyde. All right, D. The minimum concentration of iron sulfate detectable to taste in drinking water. Ooh, nice. 325 milliliters and 1.8 times 10 to the minus 6. So I'm going to go for what?
Moles of iron sulfate.
That's what it says to do. And then after that, I can go to grams of iron sulfate.
Oh yeah, because you want grams as well.
All right, what do I start with?
The molarity this time?
Okay, it doesn't matter which one we start with. 1.8 times 10 to the minus 6 moles of iron sulfate for every liter of solution. And I have 325 milliliters. Is it okay if I go 0.325 liters?
Yeah, that's okay for me.
All right, so we have to get to that point where we're comfortable doing that, going between milliliters and liters. So 1.8 times 10 to the minus 6 times 0.325. That's how many moles of iron sulfate. Let's find the molar mass of iron sulfate.
According to Wikipedia, iron sulfate or iron sulfate denotes a range of salts with the formula iron 2 sulfate XHO. These compounds exist most commonly as a heptahydrate, but several values for X are known.
Trying to make sure we got the right iron sulfate here. I think we do, 151. And we could just look over here. It's 55 plus 32 plus 1616 is 3264. Yeah, okay. All right, so 1.8 times 10 to the minus 6 times 0.325. So it's 5.8 times 10 to the minus 7. All right. And then 5.9 really, if you just round to two significant digits. Where am I at? Yeah, two significant digits, 1.8 times 10 to the minus 6. All right, and then times 151.9. So that's 8.9 times 10 to the minus 5 grams per mole. Or no, sorry, grams of the iron sulfate. Okay, that was D. Next. Why is the molarity of potassium permanganate in this solution? Or what is the molarity for potassium manganate in that solution? Well, that's easy. We've done this 100 times. We want what for molarity?
Moles per liter.
Moles of
KMNO4.
for every liter of solution, right?
Yeah.
Okay. And
0.0988.
okay, grams of potassium permanganate.
Yeah.
0.0908 grams of KMNO4 in 0.5 liters. So I have grams, but I need to get my grams to moles, don't I? So I can go grams to moles here. Molar mass of potassium permanganate. Molar mass of potassium permanganate. 158.03 for every mole. So 0.0908 divided by 0.5 divided by 158.03. So 0.001, how many significant figures?
3.
15 molar potassium permanganate.
Why did you do the liters first before the other one?
You mean this conversion factor? Why was it over here?
Yeah.
Well, I just had written the liters down kind of by accident, but it doesn't matter, right? The multiplication and division is all the same. The grams get crossed out over here. I'm in moles per liter of solution once these grams are canceled out. So, but yeah, it was a little bit different than we usually do it. Calculate the molarity of each of the following solutions. Where are we at? There we go, right?
Yeah, 55. It's 55.
I'm just double checking. Okay. Calculate the molarity of each of the following solutions. 0.195 grams of cholesterol in 0.1 liters of serum.
0.195 grams. What's the molar mass of cholesterol?
Huh. Molar mass of cholesterol, 386.65. So we have slightly different compounds for cholesterol, pretty much the same. Well, some have different number of hydrogen. No, that's the same. Yeah, that's the same. Okay, 386.65. That's how many grams there are per mole of cholesterol. And we start off with 0.195 grams of cholesterol. What are we after here?
Moles per liter.
That's right. We want the molarity. We want moles of cholesterol per liter of solution. All right, 0.195 grams cholesterol. And I can go from grams to moles. Get moles of cholesterol on top. 386.65 grams for every mole. And liter of solution, 0.1. So 0.195 divided by 386.65 divided by 0.1. 0.005 molar cholesterol. We can also call that 5 millimolar cholesterol. Okay,
Millimolar, where does that come from?
well, just like you can call something, if this was liters, you could call it 0.005 liters. No, sorry. Yes, 0.005 liters, you can call it 5 milliliters. 0.005 molar, you can call 5 millimolar, where this is a bigger M here, right? It's a unit that we use a lot in biochemistry and chemistry to express concentrations of material. So it's good to get familiar with. All right, the next one, 4.25 grams of ammonia in 0.5 liters of solution.
Ammonia, that's 17.
Okay, so you're saying molar mass of ammonia is 17 grams per mole, and we start off with 4.25 grams, and we can go from grams to moles like that, NH3, NH3, and then we're in moles of ammonia. What are we after again?
Moles of ammonia per liter of solution.
Moles of NH3 for every 1 liter of solution. And how much liters?
0.5.
0.5 liters of solution. So 4.25 divided by 17 divided by 0.5. So that's 0.5 moles per liter, or what's the millimolar?
That times 500 millimolar?
That's right, 500 millimolar ammonia. Okay, good. 1.49 kilograms of isopropyl alcohol. Molar mass of isopropyl alcohol.
According to Wikipedia, isopropyl alcohol is a colorless, flammable organic compound with a strong alcoholic odor.
1.49 kilograms. I want to know the moles of isopropyl alcohol for every liter of solution. All right. 1.49 kilograms. I can go from kilograms to grams. 1,000 grams for every 1 kilogram. Grams of isopropyl alcohol to moles of isopropyl alcohol, IPA. Okay. 60.1 for every mole. So I'm in moles of isopropyl alcohol. I want my liters of solution down below. What's my liters?
2.5.
2.5 liters of solution.
Yeah.
So 1.49 times 1,000 divided by 60.1 divided by 2.5. 9.9 molar, 9.92, 3-letter significant digits, molar isopropyl alcohol. All right, what's the last one? The D there?
Iodide.
All right, 0.029 grams of iodide, right? What's the molar mass of iodide?
126.9?
126.9 for one of them, right?
Yeah. Times 2.
So it's 253.8. So I can go from grams. I'm after what?
Molarity.
Moles of I2 for every what?
Liter of solution.
That's what molarity is, right? So I go grams to moles, 253.8 grams for every 1 mole of iodide, I2, right? And then liters of solution, how many?
1.
0.1, right?
Oh, 0.1.
0.1 liters of solution. So 0.029 divided by the molar mass divided by 0.1. Okay, 0.0014, how many significant digits? 2. So 1.1 times 10 to the minus 3 moles per liter. Okay, good stuff. Some more practice here. 56. The molarity each of these solutions. 293 grams of HCl, 666 milliliters. And I want moles of HCl for every liter of solution, right?
Yeah. You just wrote them right on top of each other that time?
Yeah, that's okay though, right? I can go from grams of HCl to moles of HCl and get my moles on top. And then I can go milliliters to liters and get my liters on the bottom. 1,000 milliliters for every liter, 36.54. Oops. 36.54 moles or grams for every mole. So 293 divided by 666 divided by 36.54 times 1,000. So 12.0 molar HCl. 12.0 molar HCl. Okay. 2.026 iron chloride. Iron what chloride?
Iron 3 chloride?
Iron 3 chloride. 0.125 liters. Okay. That's the molar mass. Molar mass of iron chloride.
According to Wikipedia,
Yeah, iron 3 car, 162.2. All right, and I'm starting off with 2.026 grams of H or FeCl3. All right, and 0.125 liters. And I need to go from grams to moles. 162.2 grams for every mole. That'll give me moles of FeCl3 for every liter of solution. So 2.026 divided by 0.125 divided by 162.2. Okay, so about 4 significant digits. So 0.09993 molar iron chloride. You follow that one?
I got it. That's pretty straightforward.
All right, what's next?
0.001 milligrams of cadmium. That's how much maximum permissible concentration of cadmium in drinking water.
Ooh, wow. So 0.001 milligrams of cadmium in 0.1 liter of water. And we want the units in molarity, right?
Moles of cadmium for every liter of solution.
0.001 milligrams of cadmium. Go from milligrams to grams, because then we can go from grams to moles, and then we can stick our liters of solution down here. Right? 1,000 milligrams for every gram, grams per mole. Cadmium ion. Look at cadmium there. Where is it at?
You don't see it? I see it.
Where's it at?
112.4.
112.4? 112.4 grams?
Yeah, for every mole.
All right. And then how many liters of solution?
0.1.
How many significant figures?
Just one.
Oh, we only got one significant figure there. So 0.001 divided by 1,000 divided by 112.4 divided by 0.1. So 8.9 or 9 times 10 to the minus 8. Molar, that is, if I express that in nanomolar, I move this over 9 times, so it will be 90 nanomolar cadmium ion in solution. 90 nanomolar. Okay. D. Saccharin in a diet soft drink. Saccharin has an interesting story. Do you remember the story of saccharin, Fred?
No, if you told me before.
I don't know if I've told you, maybe in a different life. But saccharin is, well, when I was a kid, it was a wonderful artificial flavoring, right? And everybody was so excited about it because it was so many times sweeter than sugar and it was going to save us all and blah, blah, blah. We didn't have to eat sugar anymore. And then they did some tests on rats, mice, and found that it caused cancer in mice. And so they said, no more saccharin. So they got rid of saccharin. And then about 20 years later, I was reading the ingredients on diet soda and saw that it said saccharin. And I was like, what? I thought we got rid of this. And they decided over time that that's the studies that showed that it caused cancer in rats was not applicable enough to humans. And so they said, it doesn't matter, we're going to use it anyways. And so they've been using it for a long time. The crazy thing to me was that they never told anybody, but the press made a huge deal telling everybody that saccharin was bad. You couldn't eat saccharin. But then when it came back, nobody made a fuss about it at all. So, 0.0079 grams of saccharin for every 29.6 milliliters of solution. And we want to know the moles of saccharin for every liter of solution. I have it in milliliters, and I want to go to liters, right?
That's straightforward.
Getting good at that, right? I have it in grams, and I need to go to moles.
Molar mass of saccharin?
That's right. You find the molar mass of saccharin. We have the chemical formula here, so we could add it up. Molar mass of saccharin,
183.18 grams per mole. According to Chemistry Libre text, given that saccharin has a molar mass of 183.18 grams per mole, how many saccharin molecules are in a 40.0 milligram sample of saccharin?
that's a good question too. Okay, so I'm getting 0.0015 molar saccharin. That's the solution that people like to taste in their diet sodas, apparently. Okay, so any more to do? A couple more. There's about 1 gram of calcium in 1 liter of milk. What's the molarity of calcium?
Calcium, that's the most abundant thing in milk, isn't it?
Well, not quite.
Oh, besides water?
Well, I'm not sure the concentration of proteins and fats, but it could be. 1 gram of calcium in, well, it's probably not going to be more abundant than sodium, chlorine, but we'll see. We won't see, but we'll see how much calcium there is. Gram of calcium, liter of milk. And I want to know moles per liter. All right, so I go from grams of calcium, 40.08 grams for every 1 mole of calcium. So 1 divided by 40 should be our molarity. 0.025 or 25 millimolar calcium ion in milk. What is the concentration of sodium chloride solution that will result when that many liters, that many molar solution is allowed to evaporate until the volume is reduced to 0.15 liters? Concentration of sodium solution that will result. So we're changing the volume of solution, right? So I start off with 0.15 liters and 0.556 moles per liter. But then I evaporate the volume down to 0.105 liters. So this is the opposite of a dilution problem. Do you see that?
Oh, the dilution equation.
Yeah, the dilution equation, C1V1 equals C2V2, right? And there's a nice way to regurgitate that. You can always think about the time that you were at the party drinking the punch and you created a new solution for yourself by putting it in half. Create a made-up volume and made-up concentration. Think about diluting it in half. Remember the time. And then you can regurgitate this by looking at the numbers that you put in, right? Go back to the videos if you forgot how to do that. That'll help you always remember the dilution equation. All right. But in this scenario here, we're going to take our initial volume, 0.15, our initial concentration, 0.556, and our new concentration is what we're after if we go down to a volume of 0.105. Okay? That should do it for us. 0.556 times 0.15 divided by 0.105. So our new concentration is 0.794. Okay, so we lowered the volume down, and that had to increase the concentration to keep the ratio the same. Okay, good. What's the molarity of a diluted solution when each of the following solution is given to the final volume? So we're doing a lot of dilution equations, which is great practice. C1V1 equals C2V2. The first one, we start off with a liter and 0.25 molar, and we're diluting it to 2 liters.
It's just 0.125, 1225?
0.25 divided by 2, that's right. So 1 times 0.25 divided by 2, and that's the easiest scenario, obviously. You're diluting it in half, right? So that is the scenario that you kind of want to remember in your mind. If you took some given concentration, some given volume, and diluted it to it, whoops, oh, these are switched. This was the concentration here, and this is the volume there. But some given concentration, some volume, and diluted it to a different volume, or twice the volume, you would know that the concentration will go down half as much. And if you use that scenario to regurgitate the dilution equation, that's good, right? All right. The second one, 0.5 liters, 0.5, 0.1222, 0.125 liters, or 1.25 liters. Okay, so 0.122, .1222
Yeah, 3 twos.
times 0.5 divided by 1.25. Okay, so 0.048889 will be our new concentration. All right, next one here, C, 2.35 liters and 0.35 molar.
Does it matter the units we use?
Well, whatever units you have here, which they're provided as molar and liter in this problem, if you use the same units on the other side, the new concentration we're going to find out and the new volume is 4 liters. Now, if they had said 4,000 milliliters, you can't write 4,000 here. You have to convert it so that the liters are the same here. Because whatever units here, those are the units that you're going to get over there. So 0.35 times 2.35 divided by 4. So 0.206 or 0.206 molar is the final concentration. D, 22.5 milliliters, 0.025, so 0.025 times 22.5 and divided by 100. So our new concentration for D is 0.005625, no, just two significant figures, probably, or sorry, so 5.6 millimolar, or 0.0056 molar. Okay, final concentration of the solution is produced when 225 milliliters of 0.09988 molar solution of sodium carbonate is allowed to evaporate until the volume is reduced to 45 milliliters. Okay, so C1V1, C2V2. Okay, our initial concentration 0.09988. Our initial volume 225.5. And the new solution when this gets down to, new concentration when this gets down to 45 milliliters, right? So 0.09988 divided by, or times 225.5 divided by 45. So half a molar. Okay, 65. 2-liter bottle of a solution with concentration of HCl was purchased at the General Chemistry Laboratory. The solution contains that many grams of HCl. What's the molarity of the solution?
Back to molarity?
Yep, back to molarity.
Well, if I have that many grams of HCl, I can calculate how many moles it is.
37, is that what it is?
36.
Oh yeah, 36.45 HCl. So there's 36.45 grams per mole of HCl. And then what do I do with that?
Well, you have 868.8 grams.
And now I need to go from grams of HCl to moles of HCl, right?
Yep.
And I want what?
Moles per liter.
Moles of HCl for every liter of solution, right? How many liters do we have?
2-liter bottle. What you looking at?
I just want to make sure I understood what we were doing here. So, yep, 36.45 grams. That's going to give us the moles of HCl. And there's 2-liter bottle there, so that's liters of solution on the bottom. Okay, so we just have to finish this one up here. 868.8 divided by 36.45.
So that's the grams of HCl, and now we're trying to convert it to moles?
Yeah, we converted it to moles. Now we just divide by 2, and that should be our volume of solution. So it looks like our concentration is about 12 molar HCl. And that's the concentration of concentrated HCl. You can't get HCl more concentrated in solution than about 12 molar. Okay.
What happens if you put more in?
It won't dissolve. It just kind of keeps it separated, kind of like a little bit like oil and vinegar. Or sorry, oil and water, oil and vinegar. All right. General chemistry calls for a 2 molar solution of HCl. How many milliliters of the HCl, the 11.9, the concentrated HCl, would be required to make 250 mils of 2 molar HCl? Okay. This is also a dilution equation because I'm taking my concentrated and I'm diluting it, right? Okay. So C1, my initial concentration, is my 11.9 because I'd like to know what volume of this I need to use to make my final volume. What's my final volume?
250 milliliters?
All right, so this is going to be in milliliters, 250 milliliters. And concentration is 2 molar, right? 2.
2.
Okay, so 11.9, no, 2 times 250, that's 500, divided by 11.9. So I got 42 milliliters of my concentrated HCl required. So to make my solution, I would get my bottle, do is you add acid to water. So I want 250 milliliters total volume. All right. What I would do here to make this solution, I would add about 100 milliliters of the water. And then I would add my 42 milliliters of the HCl and add it little bits at a time and swirl it and add it slowly because when you mix HCl and water, its exothermic process releases heat. And then after that's done, I've added my acid to the water. I would fill up again to 250 milliliters with as much water as necessary. Okay? All right. What volume of 0.2 molar potassium sulfate solution contains 57 grams of potassium sulfate? This is an interesting one.
What goes to the right of the equal sign?
I was just about to ask you that. What do you think goes to the right of the equal sign?
I guess it's volume.
That's right. So milliliters of the solution, right? Or maybe liters. We can go liters if we want to, but let's do milliliters is fine. Milliliters of solution. And we start with, well, we could, This one here is a little bit tricky. I'm going to let you choose what to start with.
Now let's start with the 57 grams.
So 57 grams of K2SO4. All right. And I have my molarity up there, 0.2 moles of K2SO4 for every 1 liter of solution. And I want to know liters of solution. See that? So there's my liters of solution. So I need that on top. But I have moles. So I need to go from grams to moles, and then I can use this to go from moles to liters of solution. Liters of solution will go to milliliters of solution. There's 1,000 milliliters per liter. So this is my molarity, 0.2 moles of K2SO4 for every liter of that solution. And my molar mass, potassium sulfate, molar mass of potassium sulfate.
According to Wikipedia, potassium sulfate or potassium sulfate, also called sulfate of potash, arcanite, or archaically potash of sulfur, is the inorganic compound with formula potassium sulfate, a white water-soluble solid.
So you chose right, Fred.
I did?
Yeah, because 57 grams goes to moles, and then molarity can go from moles to liters and get our milliliters on top. All right, and we solve this. 57 divided by
174.3.
divided by what?
0.2.
That's how many moles there were per every liter of solution, right?
Yeah.
Then what?
Times 1,000.
So two significant figures. Correct? Yeah, two significant figures. So what?
1.6 times 10 to the 3.
1.6 times 10 to the 3 milliliters of solution. And just in liters, it would be 1.6 liters. That's how much volume you would need to get 0.5 or 57 grams of the potassium sulfate. Now, if we had done that differently, if we had chosen, we wanted here what volume contains this many grams, so let's do liters this time. If I want to know how many liters of solution contains this many grams, and if I started with 0.2 moles of K2SO4 for every 1 liter of solution, right? Then I would say liters of solution. I want to have 57 grams of potassium sulfate ultimately. I could go from moles of K2SO4 to grams of K2SO4, and that was the 174.2. All right, and that would put me into grams per liter, and I know that I wanted to get rid of those grams. I wanted to know how much was to get 57 grams of K2SO4. So grams would cancel out. But my liters of solution would be on the bottom. Can you see that, Fred?
Is that okay?
No, it's not, because these liters of solution, that's it on top, right? So if I had started with the 0.2 moles per liter as opposed to the 57 grams up here, then I wouldn't get it to work. I wouldn't be able to get it to work like this. I'll show you one thing that you can do, but I wouldn't recommend it for general use. But if I go 0.2 times 174.2 divided by 57, all right, what I got here, so on the last one I got 1.6 times 10 to the third milliliters, or 1.6 liters. So this is not 1.6 liters, this is 0.611, but it's not, the units are per liter. So if I go 1 divided by that value, take the reciprocal of it, it'll end up giving me the 1.6 liters, right? Because it was units per liter, and now I just need the reciprocal of it. So that's something you can do, but this isn't true, that the combination of these units this way does not give us liters. It gave us 1 over liters. Okay? So it's all right if you do it the wrong way. You just stop and go back and do it the right way. Okay, so the EPA places limits on toxins. It's limited to 50 milligrams per liter. That's 50 parts per million. If an industry is discharging hexavalent chromate potassium dichromate, what is the maximum permissible molarity of that substance? Okay, so what we want to know is what is the molarity, the moles per liter of our solution if we start with 50 milligrams per liter. Look, we're already in per liter. That's great. So then we just need to go from milligrams to what?
To grams.
And then what?
Grams to moles.
Okay, that's it. You need to get to moles, right? So 50 milligrams per liter. And, no, sorry, 0.5 milligrams per liter, right?
Oh, yeah.
So there's 1,000 milligrams for every liter, or gram. What is this stuff called?
Potassium dichromate.
Molar mass of potassium dichromate.
According to Wikipedia, potassium dichromate is a common inorganic chemical reagent, most commonly used as an oxidizing agent in various laboratory and industrial applications.
So 50 divided by 1,000 divided by 294.19. Okay, so 1.7 times 10 to the minus 4 molar solution is the maximum amount of potassium dichromate that can be. What's the EPA say? Discharged into the sewer system. We would never do that, ever, on our campus, right, Fred?
Right.
No, seriously, we never would, right? We never do that with our waste. Okay, so what mass of 4% sodium hydroxide, of a 4% sodium hydroxide solution by mass contains 15 grams of sodium hydroxide?
What does a 4% mean?
That's a good question, and we're not going to be doing these very frequently at this point. Later on, Chem 106, or sorry, 1220, we'll be doing them more frequently. But a mass of a 4%, 4% means 4 grams of sodium hydroxide for every 100 grams of solution. All right, and we would like to know what mass of that solution, so grams of the solution, weighs or contains 15 grams of sodium hydroxide. Well, I don't know if you can see it, but we already have prepped this incorrectly because I have 4 grams for every 100 grams of solution. Grams of solution is on the bottom, this grams of solution is on the top.
Can't you just divide by the 15?
If I put 15 grams of sodium hydroxide down here, grams cancels out, but I still have grams of solution on the bottom. And I want grams of solution on top.
Well, what can you do?
Well, I can just start off looking for grams of solution again, but this time say every 100 grams of solution gives 4 grams of sodium hydroxide. And I want 15 grams of sodium hydroxide. So that's going to tell me how many grams of solution I need. So 100 times 15 divided by 4. Okay, so 375. And the little reciprocal trick, I mean, here we had it set up, but we ended up having the grams of solution on the bottom and we wanted them on the top. So if we had done 4 divided by 100 divided by 15, if we put 1 over that value, it would give us the same number again. So this is so 1 over grams is what this ended up being, and it was 0.1 0.00266 per gram of solution. Okay, good. 375 grams of solution. Way to go, Fred. That was a marathon homework session.
All right.